this other edition, the 26th edition of our Numerical Method 2 class. So today we are going to focus on error analysis. I hope you revised what we did last time over the weekend. I hope that over the weekend you revised what we did last time. Meaning the reading, redoing the examples, and particularly the programming part also. Because don't forget that one component of this course is programming, even though programming will mainly be tackled during assignment. When I say tackle, it means that you'll be using programming in your assignment. All right. Okay. So we are going to look at the error analysis for the trapezoidal rule. That is the composite trapezoidal rule. The error analysis for the Simpson's rule, because those are the two composite rules we have covered so far. So it will only be for those two rules. And once we cover that, I think we'll be done for today. Obviously, if there is enough time, I will introduce the concept of the rhombus integration. All right. So roughly speaking, that's what we'll be covering today. So we start with the error analysis of the trapezoidal rule. Error analysis is nothing else than the expression of the error term, right? This one. Because trapezoidal rule being a quadrature formula or quadrature rule, the definite integral can be written as the quadrature rule plus an error term. Now, the error analysis consists of evaluating, right, or finding an expression for the error term. Obviously, the derivation for this is in the theorem. If you recall the theorem, in the theorem, we obtain an approximation of this form. Okay, so let me go back. So if you remember this expression, right? So this is the expression for the actual trapezoidal rule. This one, not the composite, right? So this is, now if you rewrite the method and you apply the summation throughout, right? That summation will also come here. I hope you agree with me. Okay, let me do it for you so that you will see where that formula comes from. At least this one, you know already that this error term comes from integrating this expression of the interpolating polynomial, this one. So from there you obtain, you get the so the error term for the trapezoidal rule turns out to be negative h cubed by 12 second derivative of the function at a certain point psi So that's what we have. And you can see that on a single interval, we have this approximation. So to obtain a composite, we sum. If you recall, we sum k running from 1 to n. So that's what we perform to this one. Now let's perform the same summation to this error term. Okay, now what you realize is that when you write this in terms of I, because we have a summation of x sub k or sub whatsoever, and this psi here will also depends on the variable here of the summation. So it will be psi sub k, if of course the summation is, if we sum over k, right? Okay, let me copy this and quickly go to the, I'll only perform that example with this one. And the other one will be similar. So you will do that yourself. Okay, now let me go to the okay. So now let's look at the composite trapezoidal rule. Okay, so we know that for the trapezoidal rule itself, we have this. If you take xk minus 1 to xk, we know that this is h by 2 f sub k minus 1 plus f sub k. Minus h by 3, not h by 2, sorry, h to the 3 by 12, right? Second derivative at certain psi k. Obviously, this is in between the limit of integration. So this is in between. Right, that's what we have. Okay, so now for our trapezoidal rule, this one, the integral, we know that the integral, we split our integral. If we integrate from a to b or whatsoever, we know that this will be equal to the sum from 1 to n, like this, with this integral xk minus 1 xk fx dx. So for us to get this integral, we need to sum this entire expression, right? If I call that star, we need to sum star to get the whole integral. I sum. Now, if I do that, so summing will give us the integral from a to b fx dx, which is the sum of this. So we apply the sum here. And we know already the rule for this. We know that that's our trapezoidal Simpson rule. Obviously, that h by 2 is hi, sir. Please, I'm in a class.
All right, okay.
Okay, thanks.
Right.
Sure. So we have the summation h by 2 like this. Okay, so this one. Obviously, remember that we group this, but I'm not going to go through that. So this is our composite trapezoidal rule, this part. Now plus, okay, or minus. Okay, I can still write this h like this, like h cubed by 12. And then that I leave the summation here. Okay, so this is what we have. Right. So we have this expression. And obviously with this one, we can use a kind of mean value theorem, right? So we can replace this, all this. Because all these, do I really need, okay, of course, this one, because you can see that each of these is in between this and that, but they are all in between A and B, right? They're all between A and B. So I can still say, so I hope you understand what I'm saying. Is that this one for all of them, right? Now, among all these psi k, for the entire summation, if I look at the summation like this, I can write this. I can find a psi between A and B such that this will be true, right? I can find it. And for that, I can replace this with a psi in such a way that I still have my h by 2, and then the summation here, sub k minus 1 plus f sub k, and then minus h by h to the 3 by 12, like this. Now, this one, I can still find a psi so that this is true. Right. Right. Okay. I can still find this so that this one. Of course, the fact that this function is continuous, it is bounded, right? So this will be bounded, this is bounded, that will be bounded. So I can still find something like this. Now with this summation, now if I have that summation, if I sum now that this is constant, this will be multiplied by n. And this is exactly what I want you to see. That there is n that will multiply this expression. Right. Okay. But because here you can see that we have we took our interval AB and we partitioned it into n subintervals. Right. So we partition that in AB, the statement when we introduce a composite trapezoidal rule, this one is partitioned into n subintervals. So if it is partitioned into n subintervals, we have h, the n. You see, now this n factor can be collected from here. You see, so from that, this n will be b minus a by h. So now if we substitute this expression of n into the above, that we obtain thus we obtain that the integral from a to b fx dx, which is equal to this trapezoidal rule. I can just replace it here. Anyway, this rule, I think we call it T like this, FH, this one. Okay, now I can put here maybe C to indicate that it's a composite. Oh, it's just a notation, huh? I hope you are not. You are not disturbed by that expression. Okay, minus h to the 3 by 12, second derivative, into b minus a h. Now you can see that this h and that h Okay, so I can take this already to the other side. So I obtain minus. So the h and this, because here's h to the 1 with 3 becomes 3 minus 1, which is 2. So that will be minus h, or if I want, I can put the b minus a first. B minus a, right? Okay, now we have the h square here. Okay, all this by 12. So this is our error term. Of course, where this side is in between a and b. So you see, okay, now if we check the formula, okay, let's check the, if we check the formula, okay, now if you look at the error term, oh, that is it. It's exactly this guy. That's not witchcraft. Oh, you can see that is our error term. You can see it's exactly the same. Minus b minus a, no, minus factor, that is negative, multiply the factor of b minus a into the second derivative and h squared. So you can see, you can take that h squared and put that, it's the same thing, so it doesn't matter. So it's exactly that. You get exactly, and you can see that the our psi is in the interval AB. Right. So we have exactly the same result. Exactly. And this is our h that is subdivided into n. Sub-interval you can see here. Oh, sorry. Ooh. It's not displayed. Oh, I'm talking alone. And you can't even tell me that you don't see what I'm talking about. Oh, you too. You should have told me that I'm talking to myself. You didn't say anything. I should find you with what, mango or bamboo chicken? What should I find you with? And Janice, what should be your find?
No fancy, nothing.
Okay, so this is what I was talking about. This is the formula. It's exactly what we wrote there. Negative, and then you have b minus a here, and you have your h squared here. That h squared can come here. The position does not matter. Remember, multiplication is commutative, so I can change the position and take it here. Right. So that is it, and you can see that psi is there in the interval AB, and the interval AB actually is divided into n subintervals. H is this. So that's exactly where we extracted our n, and we substituted in our formula, And he reduced the h to the 3 to h to the 2. And then you can see that the extra b minus a is introduced when you take use this expression of h, the step side, and extract the expression of n. You see, you have exactly that result. So if you do the same, you perform exactly the same analysis as the one that I mentioned. You take the trapezoidal rule for a smaller interval, then you perform the partition and composite. It will be exactly similar. Huh? You take the error term for the original Simpson's rule and then perform the summation, proceed as I explained, and then you get this. You see that b minus a will appear because you express n in terms of h and b minus a. Exactly the way I did it. And your h to the 5 will be reduced to h to the 4. Right? Let's look. You see that in that composite Newton code, in the Newton code formula, this one, the Simpson rule, you can see that here you have h to the 5. Here. All right. Okay, so that is it. The procedure as I mentioned. And here you have 90. But the n that we are using is 2n, right? Don't forget. Because for the Simpson rule, the number of subinterval that we are using is an even number. So when you extract n from that formula, because remember that the summation is from 1 to n, where that n is half the total number of points. So meaning that when you solve for n, that same n, right, from the formula, there will be a factor of 2 that will multiply this 90, right? There will be a factor of 2 that will multiply this. And then you get 180. But some could have, so but this one was 12 before, it's still 12. Why is it that instead of 90 it's 180? That's exactly what I'm trying to explain here. Is that clear for everybody? Hmm? Are we together, guys?
Yes, sir.
Great. But if you want, you can still do the same thing, and you will see that it will give you exactly because we saw that h to the 5 will become h to the 4, right? So the power of 5 will be reduced by 1. That's what we saw with this one. From 3 it became 2, right? Obviously here, we know that the degree of precision of the trapezoidal rule is 1. So the degree here, the derivative here will not change. It will still be second derivative. The other one will still be fourth derivative. Okay, now let me quickly, if you're interested, let me quickly redo this for you, so that you will not struggle with this, with the understanding of the error analysis term. Okay, so similarly, I can write that similarly here for the Simpson rule. Composite trapezoidal. Okay, trapezoidal. So I can write here that composite Simpson. Right, so I would just say similarly. Since the error whatever is negative h by 5, a negative h to the 5 by 90, and then here we have the fourth derivative at this point, which I can replace maybe here by k, right, something like that, just to indicate that it depends on that subinterval that depends on k. So I can now write that our composite anyway, you understand what I mean? That is a composite. So I can put k here to indicate that it will depend on that, so that when you sum, okay, so now I can remove this. It's just a notation. It should not. Okay, now I put s here to indicate that this now is a composite Simpson of this. So you see, we have exactly the same summation here. Because if you recall, in the formula, we sum k running from 1 to n, where this n is half the total number of points, right? It's the total. It is no longer the total in the previous one. Then you sum here. So there will be negative here. H to the 5 by 90. And then we have this fourth derivative at this point. So similarly, as I said, that this should be, similarly, I'll just write the result here. So we have this one. H to the 5 by 90. The fourth derivative. Now, instead of depending on k here, I have that into n. Now, our h is b minus a by 2n. This is what I was talking about, a factor of 2. So from this, you can see that the n that we have here is half this. So n will be b minus a by 2h. You see, so that's the 2 that we multiply our 90 to become 180. So always bear that in mind. That's 2 here. You see. Now, if I substitute this there, so if I substitute, you agree with me that there will be negative here, b minus a, this one, because it will be in the numerator here. And then this h with that will become h to the 4th, right? And then the 4th derivative remains. Now we divide by, now you can see that these 2, because 2 here is in the denominator, you multiply this, will become 180. So you should not be scared when you look at this formula. You should not be scared. And you will need to know this error analysis formula because they are useful. Oh, I still need to. Oh, I still need to send you the second tutorial. Huh? Yeah, because the second tutorial. Oh, I have to do that. Okay, so that is it. So this is. Okay, so this is for the error analysis, right? So you have the derivation, how we obtain that from the original Simpson rule or trapezoidal rule. So that's for the composite, right? The composite rule. That's how you proceed. They are quite simple. Is everything clear? Is there anything that you don't understand?
Up to this point, it's clear, sir.
I beg your pardon?
I'm saying up to this point, it's clear.
Okay, great. Oh. Okay, so let's proceed. So the error analysis is there. We have this expression. For the Simpson, we have this expression. So you can see that we have fourth derivative h to the 4th. We have the negative b minus 8 there, and we have 180. So the rule is fourth order accurate, you can see. Whereas the other one is second order accurate. Here. Okay, now application. Okay, so for the application, this is what we have. The first example, we are using the same function as the one that we used last time. That's the same example, it's still there. This is our f. We use the same interval, 1, 6, the closing interval from 1 to 6. And we have a certain number of subdivision, 10, 20, 40, 80, 160. So here we are investigating what? The trapezoidal rule. Okay. From this expression, we can obtain the actual antiderivative of this function, which is given by this. And now if you substitute, this is the exact value. Okay, so now we can use this formula. Okay, which formula are we using here? Trapezoidal. Now, You know that the definite integral is the rule plus the error term. So from that formula, we can extract the error term. We can write error term as the definite integral, which is this value, and is given here, minus the rule. So that is our error term. So meaning that for each value of h or n, these are the h. So if we change the value of h, the rule will give us TFH for each h, and that's what you can see here. So when we have this TH, we substitute into this formula. It will give us the error term. The exact error term is this one. So the trick is we just use the formula. And we wrote the error term as the difference of the definite integral minus the rule. So when we compute, this is what the error term gives us. It's obvious if you take this, you subtract that, all this, we get this expression. Now you can see, if you observe the behavior, what we can say in terms of the number of subintervals, we are doubling the number of subintervals. See, from 10 we move to 20, so we have doubled the number of subintervals. From 20 to 40, from 40 to 90, to 80, and then from 80 to 160. So each time we double. Otherwise, when we double, what does that do to the step? We halve the step size at the same time. So you can see that this is 0.5. If I divide this by 2, it's this one. If I divide by 2, it's that, and so forth. So doubling the number of subintervals halves the steps size. And this is how you check the error, the order of accuracy of your method. So as we do that, what happened to the error term? This is the error term for the first value of h, 0.5. This is the error term. Now, if we double the number of subintervals, or if we halve the step, what do we get? Here we have 0. After the decimal point, we have 1 0 and then 1 non-zero term. So now when we have, what do we get? We get an extra 0 here, and then the non-zero term we have again. We have another extra 0 there. We have again this is not that visible. It's supposed to be 4, but we still have this 0.1, and then the 4th time, and so forth. So as we reduce, right, the successive error is reduced by approximately 1/4. Right. The successive errors are reduced by approximately 1/4. Approximately, that's why you can see that this one that did not give exactly, approximately. So, in other words, if you divide this by 1/4, you should be getting something of this magnitude. Divide again by 1/4, approximately, that's what you'll be getting. And now you can even see, we know that 16 divided by 4 is 4, right? It's approximately that. Approximately, it's not exactly. And similarly from here today. So what does that indicate? 1/4, if you look at this one, if you look at 1/4, if you compare to this one, it is this square, right? If I square this, I get this one. So, which confirms the second order accuracy of the method. Or still, if you look at this expression, this is our exact error. Sorry, exact expression, not the exact error. And now, if you look at the results here, for the first time, when you compute, if you compare this result the decimal part with this one, you see that in the decimal part, what is accurately captured is the first 1. You can see that this is 1, and you have the 1 here, right? Okay, now the next time when you perform the reduction, you half or you double. Now the next is 83. Yeah, 83. And if you look at this one, you have 86. So this one does not appear the way it appears when we do our numerical integration, numerical differentiation. Because normally with numerical differentiation for second method, it's supposed to capture 2 decimal, 2 decimal, 2 decimal. But here, the only trick that we use is the fact that the error is reduced by a factor of 1/4. So that's where we actually see the second accuracy of the method. Okay, now the second example. Okay, so this is why here you can see we also use the error term. No, here we do not even use that formula. We just use the difference. Now we are going to look at an example where we'll be applying this formula. You see the usefulness. That's why I was saying that you need to know this formula. Because in a problem similar to this second problem, you need to know the expression of the error term. So let's look at the statement. Find the number n of step size. Sorry, the number n step size, because once you have n, you apply the formula to the step size. So that the error for the Simpson rule, ES, for the Simpson rule, is less than 5 into 10 to the 9 to the negative 9 for this approximation. So we are approximating this definite integral from 2 to 7 of the function 1 by x using the Simpson rule. So if you use that Simpson rule, we know already that the error term is given by minus b minus a into fourth derivative into h to the 4 by 180. That's the formula for the trapezoidal rule. Now, in order to find the value of n such that the error is less than this, I cannot apply this directly to, I cannot say directly. It's important to understand this. I cannot impose this formula directly to epsilon, to 5 into, so I cannot write this directly, that absolute value is f h forward less than 10 to the, if I apply this, you see that in this expression, I have this fourth derivative with the psi, which I don't know. So if I do this, I will be stuck. So for this to be less than that, it is enough to impose this to the upper bound of this expression, and the upper bound that I will be using, I'll make sure that the psi, which is unknown, does not appear in the upper bound. Because even if I need to extract my n from this, you see that I cannot get rid of the psi, which is unknown. So the best way to proceed is always to find an upper bound of the error term before you impose this condition. Because if the upper bound is less than this, automatically the error term will be also less than that. And therefore, I'll be able to get the value of n. I hope it is clear. If you don't understand, let me know, I will repeat. What I'm saying is that in order for me to find the number of subinterval, I don't use this expression of E and impose directly this this constraint of the error being less than 5 into 10 to the negative 9. I don't do that. But I will import this constraint to an upper bound of the error term. So that's why the first step here is to study the variation of the derivative in order to find an upper bound. And you can see that by so doing, we succeed to obtain an upper bound of this form. You see that this upper bound does not depend on psi anymore. You see, it doesn't depend on this side. So this is independent of psi or xi. Xi, this one, xi, is independent. Now, if I impose this constraint to this upper bound, automatically the error term will be less, right? And this will still be true. Okay, now, if I use this upper bound, I can write h in terms of n from this. Remember that with the Simpson rule, we have 2n as the number of subintervals. Right? Good. So if you do that, h is given by this, then I raise it to the power of 4 and plug it back. So if you compute, this is what we have, and we impose that this upper bound should be less than the constraint. And now you see that from this, I can easily solve for my n. So if I solve that for n, we find that n has to be greater than or equal to this expression. Right. Now, I cannot take my n0 to be this, but I need to take the next larger integer, right, which is 113. So if I take n to be this expression, we are sure that we will get the result. Now, to get my h, because we want n and h, I just go back to the formula, the expression of h, and substitute the value of n, right? 2n will be 226, right? Because we multiply this by 226. Right. Now I divide 7 minus 2, which is 5, by 2 to 6, and we obtain that h is 0.0221238931381. 381. So that's the formula, the expression that we obtain. All right, so therefore the rule for that value of h will give us this expression. All right, I think we stop here for today. Please go back to the notes again and make sure that you can redo this on your own. Make sure that you can redo this on your own without looking. Maybe in the beginning, you need help to see how you study the variation, right? And you need to know why we proceed this way. Okay. Thank you for your kind attention. God bless you. And see you tomorrow afternoon.
See you, sir.
Bye-bye.